Okay, let's get started. We're already a few minutes behind. Now, whatever I've discussed in the last two lectures, the last 5 hours or so, is fairly classical. It would apply to almost any technology. And a lot of the work that I discussed was done in the 90s and maybe in the around the 3G era. Okay. And there was another thrust of activity, another burst of activity after 4G, 5G began to get deployed, and people began to ask these more complicated questions about quality of service. So today's lecture is going to be primarily on that. But before I get there, I want to review this so-called 5QI tables. Okay? And I want to particularly review this in the context of this resource type column. And the resource type column says GBR, which reads guaranteed bitrate, and non-GBR. Now, what does this mean? It does not mean that we have to guarantee a bitrate to the application. It only means that we have to give these requirements. Average over 2000 milliseconds, 10 to the power minus 2 packet error rate, 100 milliseconds packet delay budget. You cannot provide quality of service to real-time video, real-time voice, control of robots by giving them a guaranteed bitrate. You could, but that's a very wasteful way of doing it. Suppose I was to allocate a fixed bitrate to a user, which is requiring some service. Perhaps you could fix a bitrate, you could manage resources in such a way that you give that bitrate. But giving a fixed bitrate in some manner to a real-time flow, so that the real-time flow has the required quality of service, is not a good idea. It's not a good idea for two reasons. One reason is that even if you have wireline links, like in optical fiber or many years back, when you just had copper links connecting every place, you would require excessive amount of bandwidth to be reserved to be able to give these applications the required quality of service. Why is that? Because these applications do not have sustained bit rate. When a video frame comes, you get a burst of bits. Then for 20 milliseconds, there's nothing. Then again, a burst of bits, maybe a smaller burst, and then another burst of bits. If you have if you're controlling a robot, every 20 milliseconds, you will get a packet to be served. Now, suppose you reserve at all times some resource for that particular flow. It's a complete waste because you really want to be able to allocate resources when there's a need to get resources. So then wherever GBR comes, I'm not very sure, but my guess is that GBR relates to real time. Okay, this is real time sources. As I explained earlier in a slide, couple of slides before this slide, that real time sources generate an intrinsic bit rate. For example, video will have say 1.7 megabits per second for HD video, 6 point something megabits per second for slightly high quality video. That would be a sustained average bit rate. Maybe it refers to that. So one has to talk to the people who developed this table. Non-GPR to me would mean non-real time. Now, and of course, whatever requirements are there for that particular flow, one has to satisfy that, but not by giving it a guaranteed bit rate. The reason I'm saying this now so emphatically is because I'm now going to come to a mechanism for giving guaranteed bit rate, and then I'll give an example of how you give guaranteed bit rate. Okay, so my interpretation of GBR and non-GBR is real time versus non-real time. Okay. Now I'm going to show you a way. Suppose you have full buffer applications. You're downloading large amounts of data. Full buffer is a very commonly used traffic model as well among people who design protocols. These are QoS algorithms. Suppose you want to give a particular flow a guaranteed bit rate. Why would you want to do that? We'll come to an application a little later. So earlier we looked at proportional fair sharing. Proportional fair sharing, there was a utility function. For example, summation of log of the throughput of each user, adding them all up. Now, suppose in addition to giving proportional fairness across the users, you also want to give some users a guaranteed bit rate, 20 Mbps, 40 Mbps. So let's see how that is done. This is the rate region. And as you pointed out, the smoothness of the rate region is the idealization because of discrete MCSs. Really, you have a lot of points all over the place. And the rate region is not really smooth. It has, flat parts all along it. So please ignore that for now. For design, you often use certain mathematical idealizations. This is the maximum sum throughput point. Okay, this means that I'm maximizing the total throughput that the two users can achieve. This is a proportional fair. This is a proportional fair throughput point. And what we are doing is we're taking the log of the throughput of user one, a log of throughput of user zero, adding them up and maximizing that over all possible pairs of throughputs. You'll get this. Suppose in addition to being proportionally fair, I want to say I want to give user one 25 Mbps at least. I want to give a rate guaranteed user one. What does that mean? It means that I must lie. Okay, let me animate a little bit and come to a particular, yeah. So now those of you who have taken a course on optimization in education program, wherever you are, you probably know the notion of optimizing something subject to a constraint. So what we were doing earlier is we were maximizing the summation of I equal to 0 to n, suppose that n plus 1 user, utility of theta I, okay, over all the thetas in the throughput region. Okay, so we were just maximizing the entire throughput region. Okay, that means that any theta pair outside or any theta vector outside the throughput region, it cannot be included. Every theta vector inside and on the boundary is included. We're maximizing that. So in that case, the feasibility region, the region of maximizing over the entire rate region. But now I'm restricting. I'm saying that I want to give this user at least 25 Mbps. That means that any point in the rate region below this orange area is out of the question. You cannot include that. So now I must maximize this utility, which is the proportional, if U is log is the proportional fair objective, over not this entire rate region, but only over the orange region. Okay, now these little variations here is because of my drawing, but the original rate region continues, except I've drawn a line there. Now it turns out that when you do this mathematically, the optimum point moves from here to this corner. There's an important principle behind this. As this is the utility optimizing point. This is the place where you maximize summation of log theta 1 plus log theta 2 to log theta n. As I move this point away from here, utility is decreasing. But I can't operate here because I'm violating one objective. I can't operate here either because I'm violating one objective. The moment I reach here, I met that objective. Utility is dropping all the way. Okay. If I go any further, I do meet the objective of this fellow getting the desired throughput, but my utility is smaller. So the right place to operate is this corner. The utility as large as can possibly be while satisfying that particular user's objective. Okay. So that's the basic sort of idea of why this point is the optimum point. Now, the operating point seems fairly obvious here, but when you go to n dimensions, I'll show you that a little later. Visualizing that is not easy. And so one cannot simply sort of do things as it may appear from this picture. So let's see how to do that. So how do you do proportional fair scheduling while guaranteeing a few users some rate guarantees? So let's go back to our basic scheduling problem. The scheduling problem was what? That until the slot, we have given some rates to these users. These are theta 0 bar and theta 1 bar. That is history. In this particular slot, the MCSs that have been obtained by the MCS adaptation mechanism is MCS 0 and MCS 1, K referring to this particular slot. Now, to be able to do this additional task of giving a rate guarantee, I'm going to throw in a new variable. I'll explain how that comes. I'm going to call the variable new K. Okay? New K is a variable that I'll keep on maintaining, and it will drive us not to the proportional fair point, But to drive us to the other point where you get proportional fairness with rate guarantee. Let's see how that works. Okay, so the scheduler maintains another control variable, new k, which is updated in each TTI. How it's updated, I'll show you. Now, this line is the same as before. If you go back to the earlier slide, MCS ki is converted to the number of bits ki by the process I showed you earlier. So many symbols multiplied by the number of bits per symbol, and you get the number of bits. So if you schedule UEI, you get the cadets for UEI. And now how do you schedule to be able to give a guarantee of the required guarantee? You have not seen the required guarantee yet. We'll come to that. Let us suppress this UK here. Let me cover that. Whatever remains is actually the way you do proportional fair scheduling. What do you do? On the left, you find BK0, the number of bits you give to user 0 in that particular slot because of the MCS, divide by the rate the user has already got. On the right-hand side, you see BK1 upon the rate the user 1 has already got. That is the classical proportional fair scheduling. We are now adding a positive number. And this number is being added to the UE that is supposed to get the desired minimum rate. Now, intuitively, it's pretty obvious what we are doing. We are biasing this guy's scheduling metric. This is a scheduling metric, right? I take two numbers, divide them. The larger number is the one I schedule. I'm biasing this fellow's scheduling metric by a positive number. Its metric goes up, and so I will schedule it more often. Now, why am I biasing it in this particular way? Look, you can bias it in so many ways. The original metric was B over theta. I can add nu to B over theta. The original metric was B over theta. I can add nu to B plus nu over theta, or B over theta plus nu. What I'm doing is I'm taking 1 over theta, to that I'm adding the nu, closing the bracket and multiplying by B. The scheduler must do that. And this comes out of optimization theory. I won't have time to explain that. This is fairly subtle, but let's accept it as an algorithm. Algorithm is easily implementable. Where does nu come from? Let's take a look at that. But let's first of all proceed and finish the algorithm. What you do, suppose it turns out that this particular metric is higher than this metric, it means that schedule the so I'm going to use the term GFBR. That's the right term. Guaranteed flow bit rate, GFBR. So suppose this is the UE without the GFBR guarantee. I will schedule that in this case. On the other hand, if this is more than the left-hand side, then I will schedule that UE. And we update the throughputs in the usual EWMA fashion, as has already been explained earlier. Alpha is the averaging window. So we will call nu k as an index bias. Why do I say index bias? This is called an index. In scheduling, what we do is we calculate an index. Given all the information that we have in this particular slot, we calculate a number. This is an index. Every user is given an index. And then you schedule the best user. That is one typical example. So there's an index. I'm biasing the favored UE's index by a number nu k. Note that it biases the 1 over theta term. So it's biasing in a particular manner. And the amount of bias is adjusted constantly to meet the rate guarantee target. How is that done? Here's the algorithm for that. So now you're running two algorithms together. One algorithm is you compute the index, the scheduling index, compare them, and schedule the best index. Another algorithm is you calculate an index bias for every user which has a GFBR, guaranteed flow bit rate. How do you do that? So here we have only two users. One is given a rate guarantee. Here's how I do that. Take the old index bias and adjust that. This is the rate guarantee. Theta over lower bar, the rate guarantee, 25 Mbps. See how much rate we have given it so far. If that rate is more than theta 1 bar, beta is a positive constant, you reduce nu because you have a negative adjustment. If theta 1 lower bar is lower than theta 1 bar, that means you are less than 25 Mbps, you increase the index bias. The index bias is increased or decreased depending upon how different the in which direction the given rate so far is different from the guaranteed rate. Now we have two parameters in that. So every algorithm will have a structure. Every algorithm will have parameters. This algorithm has two parameters now. One parameter was the alpha. There are no other parameters. Everything else is coming from measurements. The two parameters. One parameter is alpha. Alpha is the EWMA averaging. How much time am I averaging over when computing throughput average? Beta is another parameter. It is called a learning rate parameter. We are trying to learn the correct new. What is the correct new to use? Okay. And it turns out it is important. This is, there's a fair amount of math behind this. I have no time to do that. It turns out that for the algorithm to work well, B should be much smaller than alpha. Okay. In terms of learning theory, what is happening is we are adjusting nu at a slow rate because beta is small. Beta is like if A is 0.0005, beta will be 0.000005. So it says two additional zeros after the decimal, 100 times smaller. So we are adjusting nu slowly, and we're using a slowly adjusted nu to play a role in the index bias calculation. Okay? And we adjust the bias slowly. We'll see some examples. I don't know whether I have them, but I can send you a paper on how alpha and beta affect the performance. Okay? So very simple. The original proportional fair algorithm is modified by adding a bias to a certain term in the index for users that have rate guarantees. Okay. Here's a MATLAB code. It's very easy to read. I'm leaving it here in case anybody wants to go over it. Today I have a lot of material to cover, so I'm going to go a bit faster. Okay, let's see now. This is an example of proportional fair scheduling. Users, this is a proportional fair point. We run the PF algorithm. You've seen this plot already before. I take alpha equal to 0.0005. So, P right now, 0005, 2000. And I run the algorithm. Both the rates started at 200 megabits per second. This is rate and this is time, the slot index. And quickly, in a few hundred slots, the proportional fair rate is achieved. Some variation are there because alpha is constant. Let's now throw in a rate guarantee to this same problem. I've given a rate guarantee now 150. Okay, 110 and 170. You can see 170 for UE0 and 110 for UE1. But UE1 is not happy, it can pay more and get a higher rate. So we want to push up its rate to 150. The algorithm is run now. The algorithm I just told you is run. Okay, you can see that the rate of UE1 has been pushed up from 110 to 150, and the rate of UE0 is down from 170 to 100. Okay, you can read off here 150 and 100. So the algorithm has exactly achieved the right operating point. Okay, now this is very important. So I'll send you my code if you're interested. You can play with it. The student can play with it. Apply the index bias to to B, apply the index bias to the whole thing and see what happens. You won't converge to the right point. So mathematically, we were able to establish the right way of biasing the index to get to the right point. Okay, this is the optimum point. Where's the index? The index is here floating around at around 0.013. Okay. If you've taken a course in optimization, you know what Lagrange multipliers. The Lagrange multiplier is what the index bias is. Okay. And it is around 0.013. Suppose I want to increase the rate guarantee to 170. This is 170 rate guarantee. You are pushing up the magenta line to, I think it is magenta, 170. And you push up this one even lower. Okay, so you can now go to 170. This comes to about 50. The pair of points must hug the rate boundary, cannot be anywhere else. There's no point being inside because you can always improve it. So that's the operating point for a GFBR of 170 to UE1. And of course, importantly, the Lagrange multiplier needs to go up. It's like you're giving a push. the further away you want to push the point from the proportional fair point, that will give a harder and harder push. Okay? So if the proportional fair point was here, you have to push, 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 and you get it there. And the push is given by the Lagrange multiplier. Okay? And by the way, the total throughput decreases. Remember, so if the operator is making money on total throughput, the operator is losing money. There he has to get the additional revenue from giving this person some rate guarantee. The total throughput here is 170 plus 110, 280, and you can calculate that the total throughput is falling from here to here to here. Okay. Admission control. Now we come to an important point in quality of service. Admission control. Let us see now. Clearly, you can't go below 100 and whatever is the 85 Mbps. Can't go beyond that. Suppose you have two UEs sitting out there, okay, and you want this UE comes to me and says, I want 200 Mbps. Sorry, I can't give it to you because that is not your rate. This point cannot be achieved. Let us see what happens if you try and do that. Suppose you actually put into the algorithm for the rate that you want to give to UE1. Instead of making 150, suppose I made 200. Look what happens. That particular one throughput gets stopped at 185. It can't go any further. Other UE's throughput goes down to 0. The Lagrange multiplier goes on pushing and pushing and pushing and pushing forever. It goes to infinity. Can't push. Okay? So that's what happens. So admission control is very important. How do you admit? I'm afraid it's not a very well understood problem. Okay, so not all rate guarantees are feasible. How does the operator with 100 UEs and 10 of them want rate guarantees even know how to evaluate a particular requirement? Okay, so in a wireless network, how do we determine which slice guarantees are feasible? How do we do admission control? Okay, not a very well solved problem. Okay. We are working on this, so we know some insights into this, but I'll share them offline if somebody wants. One approach which has been there for a very long time is the operator wants to maximize revenue. Let's give you an example. I won't cover the entire slide, it takes too much time. Let's suppose you have this situation. Everything that I'm saying for 2 UEs holds for, my student is not here, but she's working on any number of UEs. So there is nothing, just to illustrate. So this UE wants, I want more than 25. What does it mean? It means that I have to be somewhere here. This UE says, I want more than 80 Mbps. Then I have to be somewhere here. They're inconsistent requirements. How does the operator know? Okay, suppose the operator even knows. Suppose the operator has some magical method of knowing. How does it know which one to reject? Okay, two requirements come. You're operating a network. Two requirements come. I want 25, I want 80. Who do you accept? How do you know how? This is a simple example. Over time, you already have some GFBRs accepted. Another one comes. What do you do? Okay. One approach that operators have used classically in telecom is you have a revenue. Okay, you say, but when I accept a GFBR call of 25 Mbps or 80 Mbps, I get a certain revenue rate. Okay, and my objective, of course, as a business is to maximize the revenue rate. Okay, what I can do is I have some statistics which tell me that look, I'm going to get a very high value GFBR requirement 1 hour from now. I'm getting a low value requirement. Now I'll block this. Because if I accept this, I may not be able to accept that one. Okay, this is classical OR type of a problem. Okay, very hard problem, but I will skip it now. Okay. So this is the MATLAB code. If you want to get rate guarantee to more than one UE, here in my in the code I have made UE1 getting no rate guarantee. All the other UEs have a rate guarantee. So I'll show you the outcome of this. Suppose you have 4 UEs, 3 have rate guarantees, and 1 has no rate guarantee. Okay. Let's first look at when there's no rate guarantee for any UE. All of them began at 200. All of them converge to 100 Mbps, which is the point on the feasible rate region. I cannot draw a 4-dimensional rate region, so I have not drawn that here. But trust me, this is where you would get to if you did have the 4-dimensional rate region available to you. Okay. So this is the Lagrange multiplier is not playing any role, it is staying at 0. Now we give 120, 120, 120 as the rate guarantees. Okay, so these guys' rates from 200 came down to 120, and the non-rate guarantee UE came down 40 Mbps instead of 100. All at 100, some became 120 and some became 140 Mbps. The Lagrange multiplier, the index bias is somewhere around 0.018. Same algorithm is running, nothing more fancy than that. Different rate guarantees. One has 80 MB, one is 100 MB, one is 150 Mbps. Okay, you can see that. Where is this? 150 Mbps to this UE, 100 Mbps to this UE, 80 Mbps to this UE, and something like, I don't know, 75 Mbps remains for the other UE. The Lagrange multipliers are different now. The UE with a higher rate gets a larger push, larger index bias. This has a slightly lower index bias. This is a lower index bias. Everything is happening on its own. I'm not doing anything apart from writing the algorithm. Okay. So here in this example, all at the same distance. So if you were to draw the rate region, it will be nice and symmetric, like a part of a sphere. And all right. Now, all of this is not just theory. We've also implemented this. I want to show you what happens. So in my lab, not in my lab, but in my department, Professor Chandramurthy has a 5G lab where they are developing a OAI-based open source 5G stack. OAI is the G node B. And let me now put together two things I've already shown you. I showed you a scheduler which is loss adaptive. That is, if you lose something, you account for that by modifying the rate that the particular UE is getting. If you recall, that was a modification of this type. Take the current rate, subtract this number, okay? Where G is something which you have to keep on computing. It is the average number of reattempts that UEI makes under MCS mu I. That's why GI mu is the average number of reattempts to send the T of UEI when MCS is mu. So of course, more complicated jobs require more complicated schedulers, which require sometimes more algorithms to be run in parallel. So you have to run a measurement algorithm in parallel. And this is the index bias. So now what you're seeing is a algorithm which I call proportional fair, loss adaptive, rate guarantee, Lagrange multiplier. This is our algorithm. So PFLARGLM. So if you forget about this term, this is just what I showed you a few minutes back. You add mu to 1 over theta multiplied by the rate. If you want to be loss adaptive, you subtract this. This is the lab. In the example I'm going to show you, I can't put 100 UEs here because we don't have the facilities for that. This is the G1P. This is the BBDN radio, and behind there's another PC with a core, 5G core. And these are the two UEs. Can you see them there? There's one UE here and one UE here sitting on this equipment. And the distance is about a couple of meters, 2 or 3 meters. I'll skip all of this. Okay. This is the performance of the rate guarantee algorithm with two UEs. UE1, which is there are two Oppo phones, not normal off-the-shelf phones. UE1 is getting a rate guarantee of 200. UE0 is getting no rate guarantee. Whatever rate it gets. Okay. And this is the index bias. The index bias averages to around 0.06 10 to the power minus 3. This is going on. Something happened out here. Maybe somebody moved around the room or something. This rate tended to become low or become low. You see the index bias quickly went up, corrected it. Okay. There was an impact on the other UE. Its rate came down briefly. But this guy's rate pretty much was kept around what it should be. Okay. These are not real-time applications. I'll show you an application of this. But this is an application which requires rate guarantee for some reason. I'll show you an application. Okay. So this is the rate guarantee, works pretty well. And this is the other UE. This is the index bias. Or the mobility. This UE is moved back and forth in the room. So the engineer who's working on this project took the UE and moved it back and moved it forward again. So you can see there's almost no effect. Yeah, I'll show you something more complicated than this in the next slide. So there's no effect, and this is the actual algorithm. 3 UEs, okay? One UE is given a rate guarantee of 150, and you can see here proportional. So here we are using different algorithms. Let's not bother too much about that. Proportional fare, the 3 UEs placed in the same lab. Proportional fare throughputs are 61, 68. When you give this UE rate guarantee, you get 152 or 151 or 149. There are different loss adaptation algorithms running out here. So this is loss unadaptive, LU. So loss adaptive version 1, loss adaptive version 2. Okay. Loss adaptiveness gives you a 3 to 4% improvement in total throughput. That actually means a 3%. Suppose you have a 30 dB SNR, it says you're almost like 0.9 dB improvement. 3% times 30 dB is 0.9 dB. 3% of 30 dB is 0.9 dB. Now, this is a competing patent. It was patented some years back, and it doesn't work. You can see we implemented this algorithm in our code. The rate guarantee is not met. You get about 150. And this is the and more importantly, it provides the index bias token counter. Token counter is fluctuating all over the place, but it can even zoom in. It doesn't go anywhere near the optimum index bias. It gets 3 times 10 to the power minus 3 versus 0.06. So there are reasons why this doesn't work so well, and I can explain that offline if you're interested. So I've given it's not a very old patent, about 4 years. Okay, now let's see. We did another experiment. We took the rate guarantee UE and moved it on, we put it on a cart. This is UE0. This is the non-rate guarantee UE is kept there, and put it on a cart, and the engineer moved while being careful not to come between the base station and the UE. He moved this UE around this path. Okay. Now I'm illustrating a very interesting point here about handover. What happens if you do GFBR, and the UE is moving? Can you guarantee GFBR all the time? Let's see. Let us see now conceptually what happens. We actually can instrument that base station to get all these plots, requires some work. When the UE is at position 1, the rate region is this. Okay, you can measure the rate region. 200 Mbps is well in there. 200 Mbps is here, it can operate here. Okay, is that clear? See, UE0 is stationary. If UE0 is stationary, its point on the rate region will not change. Because what does this point mean? That point is the average rate it gets. If it's not moving, the average rate it gets will not change. Average rate it gets is if nobody else has given anything, the rate it gets will be here. The other UE is moving. So at this position 1, the rate region is here. 1 Mbps is here. So it will operate at that point. The algorithm will operate at that point. But we are moving the UVs, the movie moves away and comes to position 3. At position 3, this is the region. This point doesn't change because that UE is stationary. This UE is moving away, so its average rate drops. Now look at the rate region. In that region, you still have 200 Mbps. So now the algorithm will adapt and will give this operating point, 200 Mbps for UE1, and whatever, this is 60 Mbps for UE3. If we move the UE further away to position 6, what happens? The rate region is dropped further. 200 Mbps outside the rate region, you can't handle it anymore. Let us see what happens. This is the throughput of UE1, the rate guarantee throughput. As long as it is up to position 5, which is somewhere here, it gets the guaranteed rate. At position 6, the rate drops. Then the cart is moved back, and again, so we keep repeating the experiments. The other UE gets very poorly, very badly hit because as long as this guy was doing okay, you are at this rate region, it got about 160 Mbps. That's here. See, it's here. 200 to 160. That point, 160. So it got 160. When that UE moved away, to be able to get this UE, its rate guarantee, this UE had to be hit very badly. And so on and so forth. Okay. So what lesson do we learn out here? This lab should have one more base station here. And there should be a handover mechanism. How do you hand over GBR, GFBR calls? I don't know. What's the handover mechanism for GFBR calls? Good research problem. All right. Okay. So summary is that fair scheduling rate guarantee introduces notion of an index bias, updated guarantee. There are other algorithms available. Okay. We believe ours is the best. So it's our algorithm, so we'll say it's the best, but you can try it out. Admission control is something that we do not know how to do. PFR, RGLM, we have experience on air. We get about almost 1 dB improvement. Okay, I'm now going to come to a very important concept which 5G says it's one of the core innovations in 5G, network slicing. I have a few slides out here which are more about architecture, block diagrams, stuff in the standard. I won't spend time on that because you can read yourself. I have a lot of other things to do. I'm only going to go to one slide and I'll leave the other slides. I'll send them to you in the evening. You can look at them. Okay. If you go back to my second or third slide in the very beginning, I talked about virtualization. I think nothing but virtualization. Just like if you have a physical bunch of physical computers and you create from a virtual machine, you're creating from this a virtual service. Example, a virtual service. Okay? That is what network slicing is. By the way, virtual services in networking it actually is very established. Other examples, you can read this picture that we'll gain a little later. So what happened here is, maybe I'll orient you a bit. This is LPFS. Okay? So the N6 interface is somewhere here. This is what is called the transport between the UPF and the base station. So if you want to maintain some sort of a network virtualization, some slice, it has to be maintained everywhere across from there until the wireless. The fact is that most of this transport all the transport from the 5G network core UPF all the way to the base station is optical fiber. So there really isn't much to do there. Okay, but maybe if you're carrying that transport on wireless as well, then you may have to do something there as well. But let's assume that there really is no issue of any resource reservation all the way from the UPF along the N3 interface up to the base station. Let's come to the NG-RAN. NG-RAN is the actual wireless interface where somehow we'll see how we have created a slice for robotics. Okay, this is NSSAI-A. I don't recall what NSSAI stands for, but let's call it slice A. This is slice B, which is meant for autonomous driving. Okay, suppose there is some company like Waymo or something controlling the cars in some city. So they are controlling the cars over this slice. Okay, and this is another slice meant for your normal best effort, phones browsing or something. Okay, so here they show 3 slices. I'll stop on this here and I'll move on. Okay, so I'll skip all of this. I've given references here and I've taken the slides from one of my colleagues. Okay. Now I'm going to give you an interesting example of using a GFBR slice. I've shown you how you got a GFBR slice. Okay, suppose I want 100 megabits per second slice. I can do that now. You know how to do that. Many of you probably are hearing about FWA. It's a very old concept, but I think it's available in India now from Reliance Jio. This is a cutting from some magazine. It's Reliance Jio. It maintains consistent 5G FWA, mobile service quality, and it says somewhere here that they're using slicing to maintain the quality of service. I don't know what they do. Probably it's proprietary. Maybe somebody from industry can tell us what it does. I'm going to give my understanding of what can be done. Okay. So what's a network? What is FWA? Well, suppose there's an apartment building, or there is an enterprise somewhere that is unable to get Airtel's optical fiber into the building, and maybe it requires too much digging. Then how do they get internet access for all the employees? What you do is you subscribe to a fixed wireless access from, say, Reliance Jio. I don't know whether Airtel has that right as yet. Reliance Jio. Okay. So there's an antenna sitting on the rooftop, not a dish antenna, some other kind of antenna. And somehow from this base station, we're able to give 100 megabits per second fixed wireless access to this apartment complex. Okay. I'm told that this is a very big business, and there are some projections here which you can look at afterwards. In 2028, these are probably already old. I got them from magazine a year or so back. Okay. So the concept of a lease line is very old. ISC has a lease line from Reliance Jio. It's about, I think, 20 or 30 megabits per second lease line. In case our main line, which is, I think, 10 GB, to the National Knowledge Network fails, we use the Reliance Jio's lease line as a backup during the time they fix it. Okay? So lease line is a very old concept, and this is just a wireless lease line. So what does it mean that if I get a lease line into my campus over Reliance Jio optical fiber, what am I doing on the lease line? I'm doing my internet access. I'm doing my journal download, paper download, my YouTube browsing, WhatsApp, whatever I want to do, I'm doing on that. My Zoom calls, which are very important nowadays. This is going on that on the campus lease line. So all the normal enterprise level activities, apartment activities are happening at least there. Okay. All right. Let us now conceptualize this. So let's look at the base station. Let's look at the operator's base station that is giving the lease line to this apartment. I'm going to look at only one FWA. There's one queue behind it. Okay? There's one DRB behind it. And the apartment complex has had a negotiation with this operator that they want 150 megabits per second lease line given to them. All the other applications that this particular base station is handling are here. Okay, then let's assume that they're all best efforts. I've shown one best effort application. Is that clear now? So this is OFDMA resource grid. This resource grid is going to give the apartment complex 100 megabits per second. It's going to give best effort service to all the other phones and laptops in the area. Okay. Now, a very important concept to understand here is the notion of load of a FWA. What does load mean? Okay. Let us suppose that the users in the apartment complex are doing something. They are browsing, they are downloading web pages, they are downloading files to read on the campus, they are watching YouTube, whatever. Let's suppose that the rate at which they download files, downloading also means watching a YouTube, because essentially it's a download, but it's a download at the rate at which the YouTube itself is flowing. Okay, some people download because they want to watch it and they are, not close to the internet. Let's suppose there are 14 downloads per second. I'm just giving a number. 14 downloads per second. Each download is 10 megabits. Okay, on the average, 10 megabits. This doesn't mean every one is 10 MB, it is on the average. 10 megabits is only about 1 megabyte, 1.2 megabytes, not a very big file. Typical web pages nowadays are almost 1 megabyte, and actually more. Now, this calculation is very important to do if you're designing a FWA service. You divide this number 14 times 10. This is the rate at which bits are coming into the pipe. 14 downloads per second, 10 megabits per file. 140 megabits per second are coming into the file because of users. I can't control what they're doing. They're doing whatever they're doing. Okay? But I have only leased out a 150 megabits per second FWA, leased line. What is my occupancy? What is my load? 93.33%. What is the implication of this number 90%? We'll see that in a few minutes. The closer this load is, see, we never talked about load so far in full buffer traffic. Full buffer traffic, there's no notion of load. Everybody is full. Okay, whatever you give me, I'll be happy with. Yeah, that's not the case for browsing. It's not the case for downloading small files. There you have to worry about load. Okay, because load impacts response time. You'll see how. What happens if the download rate is 150 Mbps or more? Suppose there are, the large families and this guy, the apartment complex owner have not leased a large enough pipe. And everybody's got a laptop and TV now, you have a problem. Okay? Suppose 150 Mbps and what happens? So now suppose that the apartment complex people are all gone to the office. Maybe there are only young people there all going to the office. In the daytime, that lease line is empty. Okay. Maybe everybody is having lunch at 1 o'clock. That thing is empty. What should happen to the 150 Mbps? You should not waste it, right? It should go to the other people on the ground who are using that service. So when inactive, these other best effort UEs should get that time. How do you achieve all of this? Of course, then these best effort users will get a time varying rate, because when the people in the enterprise are active doing whatever they have to do, they get 150 Mbps. Okay, as you saw before in the rate region, these guys get a lower rate. But when they are not active, you get a higher rate. You get a higher rate. Okay? All of this should happen automatically. So what I'm going to show you is applicable to 20 FWAs and 50 UEs. There's no restriction. I'm showing you 400. Let's connect it back to our 5G QoS architecture. So let's suppose there are two DRDs. Sitting in the base station. And let's suppose that I'm putting, for the purpose of my simulation, I can simulate UEs in my program. I could, but I didn't try to do that. Suppose all the other UEs are, the traffic is 1 yard. We are serving them for 1 yard. This is DFBRD. So let's say this UE1 is zero. Not UE1, UE1 is there in the UE. So now I'll do a demonstration of what happens. Let's suppose that the load on the FWA was only 50 Mbps. Okay, maybe that particular day, there's a lot of people on holiday, people working from home, and so you have light load in the enterprise, 50 Mbps. The enterprise has leased 150 Mbps, the only 50 Mbps is the load on the enterprise that particular day. This is time, and this is the rate that the different UEs are getting. The blue is the enterprise rate. 150 Mbps is all it will get. So when it is active, I'll show you how you can see it's active. You get 150 Mbps. Other UEs get lower rate. When it's inactive, the other UEs get plenty of throughput, 300 Mbps. The other UEs on the ground. Okay? This shows activity. This is the index bias. Hidden behind these three other plots is the red plot. That red plot shows how much data is waiting in the FWA queue, in the operator's queue, in the FWA queue in the operator's base station. That is the red thing that's hiding behind. You can always see it. So that red thing is empty here. There's no queue in that particular DRB. So you go on serving the other UAs. When the queue builds up, the Lagrange multiplier builds up, and you now get 150 Mbps for the FWA. When the other queue goes down, then you can get. So you see that at 50 Mbps, I'm able to multiplex between the guaranteed rate to these, and I'm able to give, this algorithm is able to give whatever is possible to the others. Let's suppose we increase the, this is a day when they're supposed to all report for work. Friday is often Monday maybe, all report for work on that particular day, 140 Mbps load on that lease line. Okay, now look at the queues now. The FWA queue is going up. It's almost never empty. It's almost never empty. Only occasionally does by some randomness, do the others get some throughput. Okay, so this is when the others get some extra throughput. Otherwise, the FWA queue is keeping more or less busy. Okay, now I told you earlier about alpha and beta. You can play with those. So alpha is 0.05 here and beta is 0.005 here because I designed this for quick reaction. The moment the FWA queue becomes empty, give everything to the other queue. If you make alpha small, it doesn't happen very well because it takes a long time to react. So this also shows you how you can modulate, how you can choose the alpha and beta. Alpha was the EWMA averaging constant, and beta was the index bias adaptation constant. Okay, this allows this to quickly ramp up rather than ramp up slowly. Otherwise, it will take some time. It'll slowly ramp up like this. Okay. Now, what is the impact of this? What is the impact of FWA load on the users? Let us see that. You will begin to see large response times. People are browsing there. People are using that link for their work. If you get 140 Mbps, which is 93% occupancy, the users will begin to see impact on their work. Let me show you an example of that. Now, what I'm doing is, maybe I'm not doing what operators do. I'm saying that whatever guarantee of service you give a user, when the user is connected to the base station as or one of the FQIs, that is what you should also be able to give when they're a part of your FWA. Let's take this. Suppose I'm handling video on the FWA. What is the expectation of the user? Expectation of the user is there's a delay budget 100 milliseconds. The delay of the video packet should be no more than 100 milliseconds with a probability of 0.02. That's the requirement from 5G. So whether I'm attached to an FWA or whether I'm attached to 5G, I should get the same service. Let us see what happens. What happens? Your FWA queue is heavily loaded because your enterprise is drawing a lot of data. Somebody is doing a Zoom call, somebody is doing a Teams call. Video packet comes, and the video packet is waiting there. Behind a big queue. I showed you the queues. Okay? Look at the queue here. The queue is building up to 200 megabits. This is the queue, 200 megabits you can see here. Okay? Queue is large. FWA rates guarantee 150 Mbps. Download rate is 140 Mbps. Large queue buildup happens. Let us see what happens to the packet delay of the video. Remember, we wanted a 200 milliseconds delay with a probability of 2%. This is the complementary CDF. I hope you can see it from there. This is milliseconds. This is probability. Okay, what does it say? The probability that the delay exceeds 500 milliseconds is 0.55. Probability delay exceeds 1 second is 0.15. You want 0.02. 0.02 is somewhere here, 1.4 seconds. So in fact, the probability that the video packet delay exceeds 1.4 seconds is 0.02. Okay, which completely violates your video quality. You won't be able to have video interaction with this. Okay, that's why we will say turn the video off and then do the Zoom call. So there's a strong violation of the 5Q performance. If you are going to translate the 5QI performance even on FWA, it won't work. Okay, so maybe I'm doing something which operators do not do. You take 150 Mbps and then you get what you get. It's up to the consumer's own management of that. Like for example, in ISC, we turn WhatsApp off. We could even turn Zoom calls off if you want to. There is a choke point somewhere in SERC. Be done, right? Okay. Suppose you do the following. Suppose that the operator could add an additional service. Whenever a video packet comes, I put it to the front of the queue. Okay? It's probably not done, but suppose I do that. Suppose I give 2 DRBs for this particular FWA. 1 DRB for best effort, 1 DRB for real time, and then give this FWA from there. Just an idea. Now you get a dramatic improvement. I won't spend too much time on this. You find that now the amount of video, the amount of data accumulated there is just about 0.04 megabits, about 40 kilobits of data accumulated there. In spite of large queues, the video gets very good quality of service. Let me not belabor this anymore. So I'm showing you here, there are 5 videos. And you have 140 Mbps, and the videos get very good quality of service. You can take a look at it later when I send you the slides. So that's the only message here. All right. So fixed wireless access is a big opportunity. We discussed FWA, the guaranteed bit rate. So the assumption here is that FWA is being given as a guaranteed flow bit rate service by the operator. If the operator does not do what I was saying, that the operator gives priority to your video, then all that has to be done at the client end. The client has to have its own customer premise equipment and has to have in that mechanisms which will be able to give the desired quality of service to all the users in the client's office or the client's apartment complex. I do not know if that is done. Maybe Cisco has a solution, but that's the only other way. Otherwise, the operator has to be doing in the G0P, and then they can charge more for the FWA service. Okay. So I have shown you now in the previous slide how we handle, how we extend the proportional fare sharing to giving guaranteed bit rates to some users, guaranteed flow bit rates to some users. And I have shown one application of that. Maybe there are other applications which do not require guaranteed real-time performance, they only require guaranteed bit rate. Other examples that I've read about are, for example, if you want to have backups between 2 data centers, with the small data centers, there is no link between them on wireless, and other applications like that. Okay. One common application that requires wireless is when a plane enters, when a plane lands, there's a lot of data on the plane. Change the alignment of the plane. Maybe plane with India, so you want to carry Indian movies and download all those large, mentally based onto the plane. It's all wireless. It is custom to these. So these are 3 cases. Can you see? There are 3 cases where it is still being shared, but I've not gone full screen. You talked about fairness along with GPR. Okay, that's the question you're asking. So this is fairness. Okay, we accept it as fairness. Proportional fairness is fairness. So with this fair sharing, the user 0 is getting 160 Mbps. You see it here as well. The pointer visible? Yeah. And user 1 is getting 110 Mbps. We call it fair. Okay. Now, what is fair when you want to give guaranteed bit rate? Okay. I'm still solving the maximum utility problem. Maximize the log of theta 0 or log of theta 1, subject to rate guarantee for user 1. Okay? This is the operating point now. In this operating point, user 0 has fallen from here to here. Look, it went from 160 to 100. And user 1 has gone from whatever it was, 110 to 150. That's not unfairness. That is fair, but fair for the particular requirement you have put. I'm still proportionally fair with the rate guarantee. If I push this guy's rate even further, from whatever 110 to 150 to now 170, the other fellow is hurt even more. Okay? So this is not unfair. You see, first of all, I'm on the boundary. I can't go anywhere else. If I want to give this user 150 Mbps and give this user 160 Mbps, I'll have to be here. I can't be there. That is infeasible. Okay? So if you want to give some users a guaranteed bit rate, I have to hurt somebody. I have to hurt the other people. You see a lot more of this when we go to the real DBR, which I'll spend some time on now. Okay? So it's like saying there's no free lunch. You cannot give something to somebody and not take something away from somebody else. Okay? In fact, it's a good question in another way. This give and take that you do has to be done in an efficient manner. Okay? Algorithms which are good algorithms, designed with the right techniques, are ones which are efficient. They take away only the right amount and give it to somebody else. This is an algorithm like that. I could have given this fellow 150 by doing this. Sorry, let's see what is one. Yeah, I could have put 150 here. I could have given this 150. 150 and this guy gets only 50. I'm giving 150 in the best possible way. Okay. If you look at other algorithms, they will not achieve this because they're not designed with the correct steps in mind. Is it clear now that you have to take something away to be able to give the others? In fact, if you give so much, if you give this much to this user, look what happens. This guy gets 0.
So I just want to add one point to what you just discussed about, something few minutes ago. So by the time the video packet arrives at the scheduler, right? So there is no way for the system to recognize that the packet indeed belongs to a video session. Because unless the operator can afford to do deep packet inspection, there is no way. So if at all, some distinction has to be made between packets of different applications, it has to be done at the UPF.
Yeah.
Where, right, so even doing that, this job at UPF is an expensive proposition. So what usually operators do is they pack, except voice, all other TCP-based sessions into just one bearer. So what I get to hear from many people with whom I interact is that operators haven't really gone beyond two radio bearers per UE. One is a default bearer, where except voice, everything will be put into that bearer. The other bearer will be established on demand whenever there is a VoIP session.
Yeah, Sai, good point. In fact, am I audible?
Yes, I can hear you now.
Very. You have a good point, and this is something which plagues all the people who are doing research and quality of service in wireless, because there's no way that when a packet comes in from the internet, you know how to handle it. But the mechanisms are there. For example, there is a mapping from Zoom to particular toss bytes. There's a IP packets have, as you know, 5 fields: the source destination IP address, source destination port number, and then there's a toss byte. And there is a standardized mechanism to map different applications to the toss byte. Zoom has one number. I think Teams has another number. And so at least application-wise, although not video or something else, there will be indication provided the application marks it. So if the application marks it, the UPF will know. And that is the way the UPF will be able to map that particular packet or that particular flow into the specific QFI. And that QFI is now carried by the IP header, the IP tunneling header. And then when it hits the SDAP can put that packet into the appropriate DRB. Now, maybe what you're pointing out is that can one DRB have multiple 5QIs, and does the base station scheduler have the intelligence to be able to extract packets of different 5QIs and serve them? Well, conceptually, yes, but maybe because of the amount of time pressure on the scheduler to finish its work before the
Yes.
layer work, it may not want to do that. I agree with all that. So, to some extent, this is maybe looking ahead, and to some extent, it's a challenge as to how to do it. So, I'm bringing that up. But your point is very well taken. No question on that. And of course, why not do the following? Why not have two FWA, two DRBs for one FWA? Is that not done in the industry? Take an FWA and put two DRBs behind it. One real-time DRB and one best effort DRB behind it. Sai, tell me.
Yeah, so I'm not sure about FWA because, at least the places where I've been, I haven't heard about an operator supporting FWA.
Okay.
But I agree with you. Yes, one separate bearer will be there for CP.
Okay, so we'll take a short break. Not a short break, but it'll be a 30-minute break. Come back at 12. Please inform the audience. Okay, let's start now. It's 12 o'clock. We have to finish everything in about an hour's time. Should work. Okay, until now, the applications that I was considering were what would get called full buffer applications. Although in this morning's lecture, when I talked about FWA, then applications were not really full buffer. Applications involve downloads of short files, Zoom calls, and so on and so forth. But until now, I have not given any indication of how to handle real-time flows. These have all been non-real-time flows, best effort flows, as I said. Topic application aware scheduling. Although already I have given some application awareness, FWA is like an application. So the scheduler in the base station is aware that this packet is an FWA packet, it should be treated this way, and this packet is a best effort packet, it should be treated this way. Extending that to general application awareness, how is that done? So again, I'm reminding you of this picture, although Sai has told us that in practice, pretty much there'll be only two DRBs, one DRB which they handle voice, and the DRB which they handle everything. But we want to go beyond that. We're looking at using 5G in much more interesting ways than just running a public land mobile service. Okay. So again, let me remind you of this if you have forgotten that there are DRBs, the packets coming from the internet or from whatever source IMS, IP flows are coming in here. There are some rules which are placed in the UPF. How those rules come in there, I won't bother about it. There's a complicated issues there. Then those rules essentially map IP flows to QFIs. QFI is an indicator on the N3 interface. So the IP tunnel wrapper will contain the QFI. And when the packet enters the SDAP, SDAP will map QFIs to DRBs and so on and so forth. Our scheduler sits here. So whatever we are doing in these three lectures essentially is what is happening here. Okay. So this I've already talked about. Now, The abstraction that I'm going to consider is this abstraction that I will keep back here because I can see it's fairly clear. Now imagine that we want to open everything up. You have a whole variety of things happening. How do you handle that? So there is SDAP. This is a base station. I won't have much to say about uplink. Uplink is an area which I have not studied much about. I'll just give one slide on issues about uplink. I'm going to talk mainly about downlink throughout in the next remaining 1 hour. So this is the G node B. This is the 5G NR5 physical layer. The MAC scheduler sits in between the TRBs and the physical layer. Okay? All the coding, the modulation, everything is done below the scheduler. So here I've shown different service classes. Okay? This is not the same terminology as the 5QI terminology. It's not even the same terminology as the terminology in the CGPP document from 2-3 years back, performance requirement for CPS. It's a more sort of abstract terminology which classifies all possible flows into 5 different classes. Okay. One class is full buffer elastic. This is what I spend most of my time. Buffers are full. There is one queue per UE. They're doing TCP transfers, large volume transfers. And the early work I showed you on proportional fair scheduling, fairness, and so on refers to this. This is interactive transfer elastic. This is what we spent some time on today, where we are looking at flows, like for example, browsing flows. They're interactive. You browse, click a URL on your phone or your laptop, you get something down, you look at it, you get something more down, you keep browsing. Okay? Or if you are searching a journal site, you read a paper, you read an abstract, and you get another abstract, you get another paper down. So this interactive transfer elastic. Okay? Here, the same model as I mentioned this morning, the small files coming in, initiated of course by the user. When the file has come in, what happens is the model that we normally use is the user observes the file for a while. Maybe it's a paper that he or she is reading. They read the paper, browse through it, then they do another transfer. So it's interactive. Okay? And clearly the objective here is response time. You cannot just do with throughput. You're interested in response time. From the time I click on the URL until that file or that whatever image is in front of me, that's what I'm concerned about. Full buffer elastic, that's not the objective. Full buffer elastic is I'm transferring a large file, I'm doing a download or a backup or something. I want an overall through. Okay. I'm introducing 3 other classes which you can relate to some extent to the 5QI table. One is hard deadline real time. What's hard deadline real time? For example, voice over new radio, edge-based robot control. A very common paradigm these days is that the controller for a mechanical system like a robot doesn't sit in the robot itself for various reasons. The controller sits on the edge. It's maybe sitting in the core or sitting right behind the UPF. And the edge controller keeps on giving commands to the robot. Every 20 milliseconds, the small packet has to come. And I'll show you some, maybe one table a little later. And that little packet has to be delivered to the robot within 20 milliseconds before the next packet comes. Similarly, voice. Voice will be, let us say, a 200 byte packet every 20 milliseconds. And the voice packet should be delivered within so much time. It's hard deadline. Okay. So hard deadline refers to packet comes in, and the packet should be delivered at so much time. Another packet comes in, again delivered so much time. You have some flexibility. You don't have to deliver the packet when it came in. You can deliver it in the next slot, or the 4th slot, or the 7th slot. But at the 40th slot, it should have gone. That's the objective. That's hard deadline. Now, in hard deadline, the waiting packets are just one. So if 2 packets are waiting, 1 packet is already too old. The 1 packet has come, the previous one is still waiting. That means that thing is lowered, drop it. It's of no use anymore. Hard deadline will typically mean 1 packet is waiting in the queue, no more. But there are some applications we can tolerate some queuing. For example, those of you who have studied video know that it's not 1 packet that comes in. A video is basically a sequence of pictures. The camera is taking pictures. Depending upon the video quality, you will take some quality of picture. And there are these different types of frames. There's I frame, B frame, P frame. And the iframe is one which is coded exactly on the information that the picture gives right then. For example, if there is a very active scene in a movie, we'll have to encode that activity right there. And you may have a very large amount of data to be sent. And subsequent BNP frames would have less data to be sent. Okay, so the iframe may have in it 20,000, 30,000 bits. If you look at maybe a 12,000 bit packet, you may have 2 or 3 packets from that iframe. I said earlier there will be 2, 3 packets, 1 packet from each frame. Okay. The interframe time in a video is, if it's a, say a 20 FPS video, is 50 milliseconds. So when an iframe is generated, you have 50 milliseconds until you should deliver that iframe. In between, you have lots and lots of slots. What happens? The iframe is generated, it comes over the internet, maybe it comes as a bunch of packets. You're going to serve it. I can serve 1 packet now. I still have 2 packets remaining. I can serve 1 packet next. I can delay 1 packet. I can serve the 3rd packet maybe after 10 slots. So the packets are being queued for the same iframe. Okay. Maybe I may have sufficient time to play it over 2 frames. It depends upon the video quality, depends upon the delay you expect. Okay. So now the reason I've broken up this into 2 different parts, this is saying that I only want the mean delay to be bounded. On the average, make the delay bounded. It's not very practical. This is more for our own research reasons. It's like a step-by-step unraveling of the problem. This is really what, if you look at the 5QR table, this is really what they ask. They say that the probability of the packet delay being more than 200 milliseconds is bounded by 0.02. The packet, whatever it's loss rate or something. Okay. So I've now given you a range of different quality of service. Bulk transfer, only throughput is required. Interactive transfer, I require throughput, of course, but I'm really interested in response time. I mean, URL until I see it. Okay. That hard deadline is very clear. Packet comes, deliver in so much time. Then expected delay, that is the time between a packet enters until it leaves or it is delivered to the UE should have a bounded expectation. And then, of course, this is called often called the tail delay. Okay. The one thing we have to remember, and I don't have a very good answer for this. When you look at end-to-end delay between the source and the destination, it comprises many parts. Okay. Suppose I'm on a call from California to Bangalore. 70 milliseconds are being spent just on propagation delay between San Francisco and Bangalore. Okay, 70 milliseconds is a good part of the end-to-end voice quality. I don't know if you remember the international phone calls from many years back. Satellite one-way delay is 1/8 of a second, 125 milliseconds up, 125 milliseconds down for a geostationary satellite. So a quarter second this way, a quarter second back. So between the 2 speakers, there's a half-second round trip time. Very difficult to talk, if you remember, in those days. Okay. So if you're talking about a voice quality guarantee from end to end, and the guarantee is 100 milliseconds, 70 is gone in propagation delay. Then you have to also account for some buffering, some delay in the UPF, some delay in your, okay, we have made measurements on our servers in our lab. Delays within machines is fairly substantial. It's 10, 20 milliseconds, actually more sometimes. We have to account for that. All the delay is not in communication, there's also delay in software. So people, real-time OS is very important to get your end-to-end delay, So ultimately, you're probably left with only 20 milliseconds or 30 milliseconds in the 5G network, even for applications which are not hard deadline applications. Just keep that in mind. So this probability delay greater than D may not be 200, maybe only 30 milliseconds, because that is the delay budget for the wireless. You've already used up 70 milliseconds of delay budget somewhere else. Okay. All right, let's move on. Okay, so now I'm going to build up this thing step by step. I think today I only have material to cover for this combination. Let us suppose that I have only 2 classes of service, okay, which I'm handling in my network. One class of service is that I'm giving for some reason, best effort service to some users. Okay. And one class of service is where I'm giving hard deadline service to some users. Hard deadline could be voice over an hour. Okay. Suppose I want to guarantee that when a voice packet comes, 20 milliseconds later, it should be delivered. If a robot is being controlled, in fact, my examples are all about robots, that a robot control packet comes, 20 milliseconds, it should be delivered. Okay. At the same time, we are also serving best effort service. So if you go back and look at our rate region now, we know very well how to handle this. We know very well how to handle this. We have not yet talked about how to handle this. This word joint should not be taken lightly. Okay, optimum should not be taken lightly. It's optimum joint scheduling. We can do something any way we want. We can always do something. Give priority. Okay, give priority. So that's, but is that optimum joint scheduling? No. Let's look at that. Okay. So we know very well now after 2 lectures how to do this on its own. We can do proportional fair sharing, we can give rate guarantees, and so on and so forth. Now we want to add to that hard deadline real time. What we are going to do is we're going to steal some time from full buffer elastic. Okay, but we want to steal some time optimally. We don't want to take any amount of time from full buffer elastic. We want to steal time optimally. We want to achieve some sort of optimality, and you will see how that's done. While, of course, ensuring that. So, now I'm going to bring in the notion of a network slice. Suppose that I want to create in my, I have a factory, I have workers getting training, they are watching YouTube videos or factory training videos. You have CNC machines or various machines which are downloading software, depending upon the work that they have to do. And that keeps on happening. It's best effort traffic, doesn't have to be done immediately. At the same time, in the same factory, you also want to use the same 5G network to control robots. A variety of robots are there in factories. I don't think they're wireless as yet. Maybe some are, but by and large, they are on wireline. But the future is that they will be on wireless. Whether they are warehouse robots moving parcels around, and so on and so forth. Okay. Can we create a network slice in an indoor 5G network, which is meant for servicing only robots? For servicing only drones, I have a drone slice, I have a robot slice. And then I have the remaining capacity for serving best effort flows, for training, for software download, and so on. So what is the objective? Create a network slice for packet flows from an edge controller to control up to 100 robots. I'm defining the problem. While ensuring that the A and B flows suffer as little throughput loss as possible, and the 5G resources are optimally utilized. That's the whole problem. Don't waste resources. You're going to now take away some resources from the full buffer service, take it away so that they're not hurt too much. At the same time, ensure that these robots are being controlled properly. Up to 100 robots. So already this is suggesting the 101st robot is going to be blocked. Okay, so there's emission control to the slice. Okay. Now you can think of going back to the picture I showed you of slice black. So you're creating a situation like this. There is no autonomous driving slice or a controlled autonomous driving slice. It's only a robotic slice. Okay, so we're going to create in our NG-RAN a robotic slice, and we're going to create a best effort slice. Okay. Don't call it a slice, it's just remaining resources are used for best effort. Later on, you may want to think about adding an autonomous driving slice. So here is now the abstraction of that. There are a few, I'm also going to assume, for simplicity, that there is one UE per DRB. So there are M full buffer elastic flows, right? There are M users doing full buffer transfers, software downloads, whatever. Not interactive right now. We are going to work on that later. So this is full buffer elastic flows. And these are the robot control flows. I shouldn't have shown another thing here. This means this packet is lost. Okay? So in every DRD, there's only one packet waiting. This means this packet is lost. This packet has come, and this packet wasn't delivered for some reason, the front packet is lost. We have a scheduler. The scheduler is handling all the DRBs now. And there's the OFDNA grid passing every 0.5 millisecond. We are supposed to pack into the OFDNA grid the robot packets and the full buffer elastic packets. So let's now put in some details. So the HDR, the hard deadline real-time packets, after arrival will be scheduled in 20 milliseconds. We are using the numerology which has a 0.5 millisecond slot time. So every 40 slots, you must have you have packets arriving, and any packet that arrives must be delivered in 40 slots, okay, before the arrival of the next packet. Now, when you allocate resources to the HDR flows, in the resource grid, obviously I'm going to use up some resources because these red entries are for the HDR packets. Therefore, I have taken away resources from FBE, full buffer elastic. What does the reduction do to various scheduling policies? Different scheduling policies will do different things. Can I find one which will do as well as possible for full buffer elastic while giving the required quality of service to the robots? Now, some of you may be familiar with something called SPS, semi-persistent scheduling. What is SPS? SPS is that it's a perhaps a little older way of scheduling, but it has some advantages that you reserve whenever a voice packet comes in. You always reserve, as soon as the voice call starts, every 20 milliseconds, you reserve some resource. Okay, you reserve certain amount of resource elements every 20 milliseconds, whether a packet is there or not there. Whenever a voice packet comes in, it is put into that resource. It may waste resources, it may just fill it up, we don't care. And the phone is told, look for the voice packet only here, and then only there, and then only there. Okay? So it has many advantages. It reduces signaling because you only have to tell the UE once. There's this resource is reserved for you. Always look for it after 40 slots. And the UE can sleep in between. Can look for a packet at the right time and sleep in between. You'll see how it does a little later. It reduces control signaling and saves power. So our scheduling objective is this: maximize the full buffer elastic throughputs while ensuring a packet drop probability bound for HDR. Okay? What will happen is that you have a packet arrives, you keep looking for a good slot. Sometimes you may wait too long and the packet is still there in your hand and you waited too long. Okay? So essentially, we asked for a network slice for carrying up to 100 HDR call with specified QoS efficiently. And of course, emission control will be essential because once you have designed 100 slices, 100 robots, 101st voice caller robot has to be dropped. Okay. Now, in the last lecture, I think somebody in the audience or somebody online asked a question. What about reinforcement learning? The time has now come to address that question. Okay. So if you have the question in the audience, you can now focus on understanding. Let's now begin to define the problem. I'm going to define the problem a bit mathematically, not very mathematically. I'm going to give you a formulation, and then I will go on and we'll talk about results. Which give enough insight so that you understand the process and the results. So let's suppose there are 100 Westerford UEs on the ground out of the factory, doing whatever they have to do with the 5G base station. 100 robots in the factory to be controlled. Okay. Now the scheduler is faced with a very complicated state space. Earlier, the scheduler only has two things to worry about. What rate did I already give to the UEs? And what is the current channel state for the UE? Okay. Now remember, a scheduler which is scheduling 100 UEs, even in that setting, had to worry about 100 throughputs already given to 100 UEs and 100 channel conditions of these UEs. Okay. But the algorithm was very simple. It didn't require reinforcement learning and all. It gave a very simple algorithm. Calculate 100 indices, compare them, and serve the best. Or serve the best two if you want. Now, what is the situation with these 100 robots? Let's look at it. There are 100 FPUEs. Okay, let's go one by one. Don't look at the entire slide, it's too complicated. There are 100 FPUEs. There's a vector of rates we can give to them. 100 MCSs for the 100. This is the vector. A bold letter means it's a vector. That's what. So in slot K, there's a whole vector of 100 UEs whose rates I have. That's one state vector I have. Now there are 100 robots out there. Each robot may have a packet, may not have a packet. Some robot sent a packet earlier, it's already been sent. There's no packet right now. So there's a 0-1 state space of robots that have packets to be sent. So there's a 100-dimensional vector containing 0-1s, which packets are yet to be sent, which packets have already been sent. So that's another state space. If there's another state, okay. Then there are 100 robots. All 100 robots have their own channel conditions, they have their own MCSs. This is that. I've converted it to bit rate, so don't bother about it. It's okay. Yeah, so this is the channel condition for the 100 robots. TK. Now, when we are scheduling, we should be aware of how much time remains. A robot packet came in now, and there's 40 slots to go. Maybe I have not scheduled it till 20 slots, 20 more slots remain. Where do I store that? I store it in this vector. This is a 100-dimensional vector containing the remaining deadline for each packet. Now, let's understand something. Those of you who know reinforcement learning, you have to learn a certain function there. It's called a queue function. Okay, by the way, before we come to that, let's see what does the scheduler have to do. So there's a state space and there's an action space. I hope the state space is clear. The full buffer elastic rates, 100 of them. The remaining packets to be served for the robots, the robot bit rates, and the deadlines for each of these packets. The packets that are waiting out here, what deadline remains for them? Now, what is the action that the scheduler must take? Okay, the scheduler must take two actions. First of all, it must decide among all these 0-1, among all the robots who have a packet waiting for them, which one to serve. Okay, that is the vector dk. Dk will be a vector of 100 zeros and ones. Some are ones saying I must serve this packet now. Some are zeros, even if there's a one in the queue, I won't serve it now, I'll serve it later. I'm also allowing myself the action of dropping a packet. So EK is the packets that I can drop. Out of these many packets, maybe some packets are very close to deadline. Channel is poor, I don't want to bother about this packet, I'll drop it. So I'm allowing myself the action of dropping a packet. Now let's look at this. Look at the state space, how large it is. Let's look just as at the state joint space of the full buffer elastic and the robot channel states. Each robot has a 30 possible MCSs. That is 30 to the power of 100 possibilities. Each UE, full buffer elastic UE, has a 30 MCSs possible, 30 to the power of 100 possibilities there. Combination of these two have 30 to the power of 200 possibilities. Okay? So that function that in reinforcement learning we learn, QS comma A, the S is the state space, state, A is the action. This is impossible. You can't do reinforcement learning directly on this unless you do a lot of massaging the problem. Okay, so directly attacking this problem either will require some very powerful techniques, which some of you may be familiar with, but it's a problem which you should not directly take a black box. Reinforcement learning is a black box. State in, action out. Let's think about it a bit. In addition, in every slot, new packets come in. So AKA, some of the packets have not been served yet, so they of course won't come in again if we are still within the deadline. Those packets have already been served, more packets may come in. So AK is the arrival of packets in every slot. Could be up to one packet in every slot for every robot. If it's already not being served, that's fine. Now, one important thing that you have to model if you are doing reinforcement learning, you have to model the state space evolution. What happens? You have a state space, you have an action, you have a state, you have an action, you get a reward. I'll tell you about the reward, and you get another state. Keep on doing that. State, action, reward, new state, action, reward, new state. Keep on doing that. What is the new state? Well, the old number of packets in the queues is the NK, 0101 something. I've chosen to serve a few, chosen to drop a few. Subtract that. Some arrive. Some more packets arrive in the next slot. So NK plus 1 is NK minus whatever I have served or dropped plus the new packets that arrive. Very simple. This is a safe space evolution. What reward do I take for myself? Now, this is a very important thing to do. Many of these, whether you're doing machine learning, deep machine learning, whether you're doing reinforcement learning, reward plays a very important role, as you all know. Okay. How much reward do I get when I take an action in a particular slot? Remember, we have to take care of the full buffer elastic. They are supposed to get throughput. We will also take care of the fact that we're going to take away some resources from the full buffer elastic. I should also take care of the fact that I can't lose too much packets because I have a 1% or 2% or 0.5% packet loss guarantee. Okay. I want to bring all of that into this cost function. Let's see now. This is the scheduling index of full buffer elastic. What is it? Weight multiplied by rate. The weight I showed you earlier was 1 over theta, 1 over the current throughput obtained. In general, the weight is just some number W. Okay, remember I took this straight line sometimes. Maximum some throughput. The weights are all equal. 1, 1, 1, 1, 1. If you want some other preferences, you may have other weights. So Wm is the weight of user M. The rate of user M in the current slot, K is RKM. Multiply the two, you are getting the index for user M. Proportional fare will give you 1 over the throughput as the weight. I'm taking a constant rate right now because this makes the math a bit easier. We'll discuss offline how to handle proportional fare in this setting. Now, if I want to schedule the full buffer elastic in this slot, how much utility do they get from that? Is the maximum of the weighted throughputs. Okay, remember what I did was I took the rate over theta, I took the max of that. I scheduled that user. How much utility is earned? It is simply whatever utility I get 1 over theta times max of R. So this is the utility earned for full buffer elastic by scheduling the best user in terms of the weighted thing. How much utility do I lose by serving HDR packets? This is how much I lose. Look, the slot length is T. How much time is used up by the HDR flows? Well, I take the whole vector of zeros and ones that I serve. Dk is that vector. I multiply each one by the amount of time it takes. That's a dot product. So it's dk times dot tk. This adds up all the time taken by the full buffer elastic by the HDR flows. So dk dot tk, tk is the rate, is the time that each, actually this is time and rate interchangeably. Time that each robot takes per bit served and actually per packet served. And dk is whether a packet is served or not. This is so the slot time minus time taken for the robots, time remaining, divided by t is the fraction. So this is a fraction of time that remains to serve the full buffer elastic. So this is the utility that you get in the slot for the full buffer elastic after serving the robots. Okay. So this is how I brought together the utility for the full buffer elastic and the service that I've given the robots. I haven't optimized yet. I'm saying if you serve dk, then what do? We must also, I could just lose all the robot packets. Then great, I'm getting all the utility. I must penalize the fact that I can't lose too many packets. I put a penalty here. Okay. 1 is a vector of all ones. EK is what I have dropped, 0, 1, 0, 0. I've dropped some packets. So this is the total number of packets lost from the robots. Lambda is the penalty I'm putting on packet loss. So lambda times drop the penalty for dropping packets. So this is the reward, this is the penalty. So this is the overall reward per slot that we're going to use to drive our, if you want, algorithm, reinforcement learning, or whatever you want to do, you'll drive it by that. What's the objective? Over time, maximize the average reward. Okay. So what is the problem to be solved? CK is this one. CK is the reward you get in a particular slot for the action you took. What was the action we took? We took the action, serve these robot packets, drop these robot packets. In the remaining time, apply the full buffer elastic policy, and just keep on doing that. The policy gives you whom to serve, and whatever remaining time you go into the robot policy, or the full buffer policy. So CK is the reward I get in slot K. I put a little symbol here, pi. Pi is a term we always use for policy. What's the policy? What's the policy? If you do reinforcement learning, when you get a Q function, it defines the policy. What you do is you get a QS comma A. Then you just for every state find the A which maximizes QSA. That's the policy. The mapping from state to action. Okay, policy is mapping from state to action. What do I do? The policy is the mapping from this to action. That's it. In such a way that over time, this average reward is maximized. That's the problem. Okay? So this is a well-defined problem. You can handle it in a variety of ways. So pi maps states to actions. Pi can be a variety of things. You can have your own pi, you can have your own pi, you can have your own pi. What is a good pi? It's what we're going to look at now. So under certain conditions on the channel evolution, the channel evolution is Markov, for example. Then you can use Markov decision theory. Markov decision theory is a precursor to reinforcement learning. Reinforcement learning is an algorithm to solve MDP problems. So this is a general black box algorithm which does not need you to fully define the MDP problem, but it solves it for you by learning. But let us not get into that right now. Let us come up with some simple policies in some manner which I'll explain to you to get things started, to get things understood. Okay, let's look at that first. So what we do is, instead of solving the entire general problem, this is a methodology that I'm trying to get you engaged with. Instead of solving the entire general problem, we can solve the entire general problem in two ways. Okay, at breakfast time, I just think of something over coffee, I'll do this policy. One way of doing things. One way of doing things is that you've been trained in a particular way. Let's systematically approach the problem. Let's make some simplifications. Let's make some assumptions and get a good policy. And then see whether we can then go and try to get a better policy. So here is one simplification that we have tried. See, these robots are sending, the controller is sending packets to the robot asynchronously. Whenever it is time for the robot, it sends the packet. Let us synchronize that. Synchronize that. The robot, the IH controller sends all the packets.
Just to fix.
Let
to fix.
What happened?
Yes.
Oh, okay. There's a question, okay? Where's the question? If you can speak it out or audio. Yeah, okay. In fact, the way you would solve it is by discounted reward only. What I'm telling you is actually done by discounted reward. And what we do is discounted reward is good because the channel is changing over time. Discounted reward is easier to handle, but average reward is really what you want. So discounted reward is perfectly fine. You can, in fact, the way we solve the problem that I'm telling you here is by discounted reward. Okay. So Discounted reward, you just put a gamma to the power of k here. Old rewards are not so important as current rewards. Same as EWMA. Old throughputs are not as important as current throughputs. So we assume that everything comes together and we can now solve the problem. It turns out we can actually solve the Markov distribution problem using discounted rewards. We get an answer which I'll show you. All right, now let me get to what the answers look like and how we can get to some interesting answers we can actually implement. Here is what the answer looks like, which I just told you, which we get from simplifying the problem by synchronizing the arrivals. Here is the policy. It turns out that there are numbers you have to compute, tau Li. You have to compute these numbers. How they computed, we will not spend time on out here. You compute the number. What does it say? In slot L, for robot I, there is a number, a threshold, which you store in the base station. We compute the current index for the full buffer elastic, WMRLM. We take that threshold, which we have found a priori, multiply by the current slot time, divide by the full buffer elastic index, and see if the time required for this robot's packet is smaller than that. Okay. If so, we serve the packet. And we do this for all the packets in a particular slot. Move on to the next slot. Okay. In the next slot, this tau will change because you moved one slot further, and so on and so forth. Notice that here we are combining in the algorithm, we are combining the current state of the full buffer elastic along with the current state of the robots. We call this joint scheduling. I won't give you examples of this right now. It is computationally hard. And we'll talk about it maybe some other time. I'm going to talk about a simpler policy. Okay, this particular policy does have this in it. So this is a simplification of this policy, which you can actually implement. It doesn't require any calculation of these thresholds, which require channel state. To calculate threshold, we require channel state knowledge, require some integrations and all that. We won't bother about that. Let's just propose this policy. What does this say? Look, if I turn this around from a less than to a greater than, just transpose the t here. Transpose the t here along with u. Transpose tau Li here. And pull out from that the residual time remaining to serve this packet. I'll get this term. What is this term saying? This term is putting in the denominator the quality of the full buffer elastic. Putting in the denominator the time required to serve the robot. Putting in the denominator the remaining time to be scheduled. So look what happens. If the full buffer elastic channels are very good, this number is large, it pulls the index down. If the channel quality for the robot is very good, t is small, it pulls this index down. If the time remaining for the robot to be served is small, delta is small, it pulls the index down. Okay. Sorry, it pulls the index up. I'm sorry, I should have said the other way around. Yeah, if the channel quality of the robots is good, means t is small. If the remaining time is small, it pulls the index up. If the channel quality of the full buffer elastic is good, pulls the index down. Compare that with the threshold. What is this saying? It is saying that if the full buffer elastic have a very good channel, I would prefer to serve them now because this threshold is small. I will not cross over this threshold. This index is small, I won't cross over this threshold. On the other hand, if the channel quality of the full buffer elastic is not very good, U is small, T is very small, delta is small, the index goes up, I should schedule. So this scheduler is favoring very high quality full buffer elastic channels. When the full buffer elastic channels are not very high quality, it's favoring the service of the robot. Okay. So we call this RDR scheduling because T is really 1 over R, 1 over the rate. So R goes in the top, rate to deadline ratio scheduling. And joint scheduling, we'll put a U here. Layered scheduling, we will not put a U here. And I'll show you results for layered scheduling on the next slide. So basically, here is the process we have followed. We formulate the problem formally. we don't simply jump to heuristics. That's the first thing. Formulate the problem formally, maybe simplify it somewhat, try to solve the problem. You come up with an algorithm. Algorithm may be very complicated because it requires too much information. Simplify it further to be similar in performance, but motivated from the algorithm, then try it out. Now, one other thing I should say here is, if the algorithm works well, it gives you a starting point. Reinforcement learning is an iterative algorithm. You should start somewhere. You can start from zero, nothing. You have a huge state space to explore. You start from some algorithm which is reasonably good. Now you can apply reinforcement learning and get to a better algorithm. Rather than start RL from the beginning, complete blank slate, start RL from something which is reasonably good. Maybe you'll get to something better, faster. Okay. So I'll show you some experiments now. Okay, I have some time remaining. So this is a 250 watt indoor G node B. The 40 megahertz, relatively small, but probably good enough for indoor service. Noise floor is minus 93.8. 43.3 dB is the, forget about this. The center frequency comes in here. Path loss exponent is 3. Rayleigh fading, Shannon formula. Channel coherence time is 0.5 milliseconds. This is IID. We are working on making it vegan also for non-IID. Node locations are, so we take a 100 meter to 500 meter range, distribute on that 100 full buffer elastic users, and 100 robots. 100 robots distributed over a large, like a yard or something. Okay, that's the setup. We compare 3 schedulers. SPI scheduling, what SPI scheduling does is, for each robot, it reserves some, starting from the first packet, it reserves every 40 slots, some time to serve that robot's packet. And this, of course, saves the robot's energy, but it is very wasteful of wireless capacity, as you will see. We look at service on arrival. Then we don't reserve capacity. We don't reserve resources for the robot. When a packet comes in for the robot, we just serve it right then. Next time a packet comes to the robot, we serve it right then. Voice packet comes in, we serve it in that particular slot. Next slot, when a packet comes in, serve it in that slot. We'll compare these two with the policy which I have just defined for you. 1 over T delta. In every slot, take all the waiting robots. Look at the amount of time it takes to serve that packet. Look at the residual delay for the packet. Multiply and then take the reciprocal of that. Compare that with the threshold. Okay. If this threshold is very large, you will throw away all the packets. Okay. The threshold is very small, you will accept all the packets. We then tune the threshold, epsilon. The threshold is tuned to achieve a packet loss probability of 0.01. Where is the tuning done? This is an ideal place. This is an ideal algorithm put in the RIC. At least ORAN has this notion of a near real-time RIC. So we offload this activity to the near real-time RIC. It doesn't have to be done in every slot. We can do it every 40 slots. We can do it every 500 slots, depending upon the responsiveness you want. So what happens is some data goes to the near real-time RIC. I'll tell you what happens. In the near real-time RIC, the RIC keeps computing the gamma and feeding it back to the scheduler, which then goes on and applying the scheduler to the policy. Policy is very simple. It looks at the robot channel conditions, the robot residual delay, and uses that in comparison to the threshold to service. Okay. Let us now see some results. What I'm plotting here is, so you have 100 UEs, 100 full buffer UEs spread over 100 to 500 meters uniformly. 100 robots also spread over the same region. I've already told you about all this. I'm plotting here the throughput of the full buffer elastic as a function of their SNR. So UEs that are very close to the border, the boundary, will have low SNRs, like here it is minus 4 dBm. UEs which are very far from the very close to the border, to the inner border, will have 14 dBm. Okay. So this is the range of SNR UEs. This is the throughput. Let us first of all look at what happens if there were no robots. This I have already shown you this plot earlier, maybe at the end of the last lecture. This is the proportional fair profile. Okay, a UE which is at about 13 dBm, very close to the inner region, the inner 100 meter, is going to get about a 3 Mbps bit rate. Okay? A UE which is very close to the border will get about a 500 kilobit per second bit rate. Maybe it's adequate for their application. Otherwise, we increase the power, increase the bandwidth. This dotted line here is an analytical approximation. I will not bother about that. Now, our cost function was what? Our cost function was that we look at the amount of utility we are giving to the full buffer elastic. We are counting how much utility we take away from that by scheduling the robots. Okay. So what is the remaining utility, the remaining throughput the full buffer elastic gets after serving robots? Let us now see what different algorithms do. This is SPS. The throughput has come down dramatically. Why is that? Because in SPS, we're simply throwing away resources. We're reserving resources in such a way that no matter what the channel condition of the robot, you're getting 1% packet loss and just wasting resources. The channel condition is very good. You still reserve that much. There are advantages. You have less downlink signaling load. DCI load is less. And your UE can go to sleep. It's called DTX in the industry. Your transmission can be discontinuous. You can do DTX and the UV can save a lot of power. This is serve on arrival. Very simple modification where a packet, when it comes from the robot, is immediately served. And whatever channel condition there currently is, and whenever a packet comes in, it is immediately served. Okay. So just that much has the improvement. Now, of course, there's DCI required because now the base station should tell the UE where the packet is for it. Can't signal the UE once in the beginning of the call and not signal again, ever again, because SPS can allow that. SOA will require DCI signaling every time the packet is served and comes in. So this is more DCI than this. But the UE can still go to sleep because it has look at the channel only when, look at the slot only when the next packet has to come. This is the policy I just introduced to you. What it does is it takes the current channel condition, takes the residual time compared with the threshold. Threshold is tuned to this epsilon 0.01. And we get this improvement from here to here. Okay. Now look at this improvement, how it looks like. How to think about this improvement. A UE that was at 10 dB SNR with SOA was getting about 1.5 Mbps. Okay. By reducing its SNR by about 3 or 4 dB, you could still get 1.5 Mbps if you simply follow this policy. A simple policy change can substantially help. Almost 3 dB improvement in power can be used to serve that again. Okay. Now the other algorithm I mentioned where we put a U in here, should be able to push this curve up somewhere closer. We don't have that right now, so we'll come back to that maybe some other time. And by the way, this gamma epsilon is being tuned every 500 slots, right? 500 slot and at a slow time scale. Now, I'm going to show you something more. That plot I just showed you is here now. These are all the rates that are the full buffer elastic rates, accounting for whatever loss was there because of HTR. This is the profile of adaptation of the gamma, the threshold. Okay. On the x-axis is the update index. On the y-axis is the threshold. The threshold started at about 0.01, quickly adapted. This is not very quick because this is a lot of time that is elapsed out here, maybe about 3 or 4 minutes. And here it is fixed. It has come to some steady state value. This is the loss probability that the robot packets are getting. There was some fluctuation for a couple of minutes, and then the loss probability stabilized to 0.01. Okay, so the gamma threshold was adapted quickly, and the loss probability stabilized to 0.01. But you can ask the question, this is only the average loss probability. There's some robots are near the boundary, near the inner boundary, some are near the outer boundary. Are we fair across them? Are some robots getting a very high loss rate? Some robots are getting a very low loss rate. Is that happening? That indeed is happening. For example, robots with a very low SNR are getting almost 10% loss rate. See, this is there. So this is the loss rate per robot. Loss rate by SNR. Robots which have a 0 dBm SNR are getting 10 to the power minus 4 loss rate. And further on, I have not plotted all of that. Some robots which are near 12, 13 dB probably getting no loss at all. So this is a very loss unfair algorithm. Okay, what do we do? How do we make the algorithm loss fair? Okay. Now I want to add another point here about algorithm design. You can now throw something more at reinforcement learning. We have another complicated problem to work with. But the process that we have followed of systematically building up the algorithm gives us some insight. And now we can actually make it loss fair. Now you can go from there with reinforcement learning and get a better algorithm. And we make it loss fair. You see, it is not completely loss fair, but you can see now the robots near the outer boundary are getting about 0.02% loss rate rather than 1%. And whereas those that were getting almost no loss are getting about 10%, 1 in 1,000 loss rate. Okay, the spread is much less. The spread is shown out here. 2 times 10 to the power minus 2 to 2 times 10 to the power minus 3. Maybe there's a better way to improve it further, and we can try to do that. Okay. So there are many aspects of performance. And some refined performance measures must be looked at. Okay, so I'm going to move on to the last topic. I've only got 5 minutes. I'm only going to give you a glimpse of this. But this is really the future. This is not done. I think that what I've showed you right now is also not done. Is it done in practice? This detailed kind of quality of service at the level of flows. I think this is something which is still emerging. Industrial wireless is still emerging. So this is something which maybe, but I know that a lot of research is happening. People are writing papers about this. And this is some work that I wanted to share with you. It gives you a perspective about the area. Now, what I'm going to come to next is how do you schedule an entire network? Okay. You don't have scheduling only one base station. How do you schedule an entire network? So I'm going to only give you a glimpse of this because this is going to take another half an hour. I have many slides. And it is in this context that you bring machine learning in. I have slides for that in this section. I'm going to give it to you. You can read it. How you can bring machine learning into scheduling. All right? Okay. Here's a very simple problem. There is 2 UEs at the edge of 2 base stations. Only 2 UEs. This UE is associated with this base station. This UE with this base station. Okay? When you schedule this UE all by itself, it's getting power only from there. Okay? It's getting power only from there. Signal power only from there. Schedule this UE only from this base station and get signal power only from here. Schedule them together, you get signal power here, interference power from here, that is shown by this arrow. When you schedule this UV along with this UV, signal power from here, interference power from here. Okay? Now what do? You schedule UE0 alone, you schedule UE1 alone, and you schedule UE0 and UE1 together. The scheduler has now 3 actions. You remember when there were 2 UEs in one base station, there were 2 actions. Schedule UE0, schedule UE1. Okay? Now there are 3 actions. If you have 100 UEs here and 100 UEs there, you can see how complicated it will become. Impossible to do. Now you have only three actions to. How do you choose which action to take when you have these things to show? Even in a factory, you can have two base stations and a robot, two robots at the edge. What do you do? Okay. We're going to make a simplification. I think this is a fact. The TTIs across the base station are synchronized. Yeah. Universal frequency reuse. Okay. 3.5 megahertz. Okay. All of them are using the same bandwidth. That's the way modern cellular works. You don't do the old 2G style frequency planning. Although intercell frequency coordination is done, maybe you will carve out from the periphery of the cell, you will give less frequencies there. I think that's probably what is done in practice, but this may be the future. Okay. So I'm just bringing to you some possibilities. So what they will do is they will take a large cell and they will reserve some carriers only, all the carriers for the center, and a fewer carriers for the periphery. And these peripheries are frequency planned. That's one possibility. Okay. Let's take this problem. I'm just giving you a complexity because as you go in to MIMO, as you go to multiple cell scheduling, joint scheduling, you have a certain problem which I want to bring out now. I'll leave it at that. Draw no complexity. So you can either serve UE alone, you can serve UE1 alone, you can serve UE0 and UE1 together. Now, what happens to our scheduling indices? What happens to them? The scheduling index was you take UE0's current rate, you take UE0's MCS, divide, and whichever one is the better, you serve it. It turns out that the correct, so now what is happening? You have the two UE's throughputs. This is, of course, a joint scheduler. This is not a scheduler working at each base station. There's something sitting in the middle doing the scheduling. That thing in the middle has the two throughputs. It has the two MCSs. It also has the joint MCSs. If I schedule this UE here and that UE there, what MCS will this UE be able to support? What MCS will that UE be able to support? Okay. This is actually very much what you do in MIMO. Okay. So now let's see what happens. Let's tell you how you go about doing this. You now have to compute three indices. This is the old index. The bit rate, the number of bits this UE will get alone, divided by its throughput. This is what this UE will get alone, divided by its throughput. Now you have to also compute a joint index. This is the way the joint index turns out. You take, suppose you want to schedule them together. Take the joint MCS. What MCS you can support for this UE when they're together? Divide by its throughput. For this UE together, divide by its throughput, add them. Okay? And then take the best of these three. If this is higher, schedule them together. This is higher, schedule this. This is higher, schedule this. If you want to do this for a large number of UEs, it's impossible. Okay. So I'm not, this MATLAB code is bigger now. You can actually plot a rate region. You can actually find the proportional fair point because there are only two UEs. There are only two rates. There's a rate region, proportional fair point. You can actually show that the algorithm will drive to proportional fair point. All of that works. I'm going to skip all of this. You can do even rate guarantees. I'll skip all of this. I'm just going to come to my last slide for today, maybe the last but one slide. Look at the problem if you're going to schedule 99 UEs in each base station. Okay. You have 99 plus one action. Even if you schedule only one UE, you have 100 actions. What are the 100 actions? Schedule any UE, schedule no UE. 100 actions here. So 100 actions for that base station. You have -1 because you want to schedule somebody. 100 times 100, which is a large number, -1, so you have 999, 999, 4 nines possible actions. So in that scheduling slot, you have to compare 9999 actions. Not possible to do that in practice. Okay. You also need a lot of measurements now, interference measurements, You want to get usable bit rates if you schedule things together, not very easy to do. Okay. So I'm going to now come to, so what people have tried is this. They get all the powers, the receive powers from all the, for all possible activation sets from both the base stations. In fact, here they have done it for seven cells, and they have a deep neural network, and they're able to schedule, given some lot of measurements, they're able to schedule these UEs across the base stations. All of this is really ongoing work, and this is not our work. It is from this paper. Somewhere here I mentioned the paper. This paper here. So deep neural network interference management. It's already fairly old. A lot of activities in applying deep neural networks and reinforcement learning and deep reinforcement learning to scheduling. Okay, so I'll skip all of this, and maybe I'll just mention this uplink scheduling. The uplink scheduler sits in the G node B. Okay, so whether you're scheduling uplink, scheduling downlink, is all happening in the G node B. The main differences are the UE buffers, as they are visible in the case of the G node B. Downlink scheduling, the UE buffers, the G node B, the DRB buffers are known to the G node. The UE buffers are not seen by the G node. So every now and then, the UE send a ground request by what's called a PUCCH, packet uplink control channel. Okay? So in this ground request, when the UE send up the G node B, there would be some buffer status report, a report of the buffer size that it has. Due to the time division duplexing, out of 10 slots, 6 are downlink, the 7th slot is shared, and 6 are downlink, 7 slots shared, and 3 for uplink. There are DDD delays, which we have to, of course, live with. Then there's the other issue, which is complicated, that the UE may not have sufficient power to send the data up. So along with the buffer status report, we'll also send a power headroom. How much power do I have to send the data right now? So then when the UE schedules, to schedule keeping in mind the quality of service, the amount of queue that's available, and how much power the UE is allowing itself to use for transmission. So it's a more complicated decision problem. And so all right. The other issue that I have not covered at all in my talk in my lectures are downlink full buffer scheduling with multiple UEs being scheduled per transport block. Now, some measurements that we have made and some experience we have, scheduling, if you recall the calculation I showed you for 100 megahertz bandwidth and 100 megahertz bandwidth, I think 100 megahertz was what matters there, was that you could fit about 18 or so packets, 16 packets I remember now, into one transport block. Okay. Serving 16 packets of one transport block is not a bad idea. Trying to break up the transport block and serve one packet per UE for full buffer elastic is not a good idea. Okay, because you have too much DCI overhead. Probably quality will handle 16 DCIs. In the DCI space that you have, you will only be able to handle 4 or 5 DCIs. So I think the recommendation is put one full buffer elastic and fill up maybe 3 or 4 or 5 downlink hard real-time packets in the remaining space. So I think that's about all I can say about it. But when you are doing uplink scheduling, because of the UE's power headroom, you may not be able to fill up the transport block, uplink transport block, with only data from one DRB, from one UE. So you may want to schedule many UEs in one transport block in the upstream. Okay, so I think I'll stop here now. The RAN throughput region is a core concept. If you recall, even the design of the hard deadline real-time scheduling was done keeping in mind that rate region. If you are sharing that, if you're sharing the resources with full buffer elastic, with interactive real-time, interactive elastic, and real-time. If you only have real-time, don't bother about the rate region. Then you have to schedule things, in a different manner. The provision of QoS is all about RAN scheduling. You have to coordinate with power control, beamforming, and interference of projects, which I have not spoken at all about. Okay. I think I'll stop here. I hope I've given you some feel for the problems, and you can then, based upon this, build upon your understanding through reading. And those of you who are more practical, maybe even building something. Thank you all for listening, offline and online.